digesting any of this stuff. So what ends up happening is kids who take the regular geometry class here, regular high school, when you see these contest questions, you're like, whoa, I didn't learn how to do that. But you really did learn how to do that, but you were able to get an A in your geometry class without being able to apply those things, right? So like, for example, you had similar triangle questions in your geometry class, but they made it so darn easy because they drew the two triangles. They would be like, oh, look, this triangle is similar to this triangle. And this is 3, 4, 5, and this is 6. What is this and what is this, right? So they would do things like that, right? So we're like so obvious, right? That like the use of what you're supposed to do. And then the big section was called similar triangles. And then they'd have 2 pictures, and then you'd have 5 problems that look all like this, right? So you get an A on these problems, but then when similar triangles come up and it's the exact same math, just make a ratio of 2 things, you don't see it, okay? And so what I want to do is each of these things are things that you learn in the regular, even if you're not in honors, in regular geometry, they go over maybe all of this except for these last 2 things. Yeah. The median, I'll tell you what I mean by the median rule in just a minute. They did go over it in my regular geometry class, but I don't know if they still did. But anyway, so these are 5 specific rules that I have set up. What I'm going to first do is I'm going to quickly recap the rules, which I'm assuming that everyone probably has seen if you've taken the regular geometry class. But you probably either A, didn't think much of it, or you could have forgotten it. But I'm hoping that many of you remember. So similar triangles, basically similar triangles means that all 3 angles are the same, so the shape is just like a blown up version, right? A scale model, right? So what that basically means in terms of scale models is if I've got a triangle that's a scale model and the shape is the exact same. So if I've got 2 corresponding sides, and I know what they are, then that's the ratio of the lengths. So let's label this X and Y, let's say, then 6 over 3 is going to equal X over 4 is equal to Y over 5. Okay? And so, obviously, it's pretty easy to solve for X and Y once you have that sort of situation. So at the end of the day, that's all similar triangles is. 2 things you need to know about similar triangles. 1, right, that the ratios of the sides are linear. The second thing you need to know is the areas are ratio squared. So for example, if this area is 6, we know that this area is 6 because 3, 4, 5 is Pythagorean triple. Okay. Then what you're going to find is if the ratio, right, so L1 to L1 prime, if that is equal to 2, then A prime, sorry, I'm doing my, let's do it this way. Yes, let's do it this way. So L1 prime is the 6, L1 is the 3, the area for this one that matches that one is 6. The A prime is going to basically be A times this ratio squared, right? So the area of this guy is going to be 24 in this case. Similarly, if we had a 9, right, if I give you another similar triangle and this is 9, then this area is going to be 6 times 3 squared because the ratio between this 9 and this 3 is 3. So that's pretty much all you got to know about similar triangles. Hey, Sean. All you got to know about similar triangles is if they're the same shape, how do I prove that 2 triangles are similar? I just need to know that all 3 angles are the same. Once I can prove that, then the sides are at a linear ratio, the areas are at linear ratio squared, right, to the square ratio. Okay, any questions about that? So that's all you need to know in terms of the formula for similar triangles. And what I find is that nearly every contest, probably that at least the AMCs, there's at least one question where you can solve it using similar triangles, and it's a ton easier than using like crazy trig functions. Okay, good? All right. Can I erase because the board is small? Okay, next, angle bisector rule. So bisector means you divide in 2. So if I've got, let's see here, let's say something like this. So let's say that this is theta and this is theta 2, and let's say that this is A and this is B. Okay, all right. So then what we know is the area here is equal to A over A plus B of the whole area. And the area here is equal to B over A plus B of the whole area. Okay. So for those of you who've had trigonometry, there's a geometry way to prove this, which I actually don't remember. The way that I reprove this, the super easy way to reprove this. So if you forget this, what you do, just put that side in there, C. The area of the left is 1/2 AC sine theta. The area of the right is 1/2 BC sine theta, right? So this is like A1, make this like area 1, make this area 2, and this is area 2. If you divide these two together, A1 divided by A2, you get 1/2 AC sine theta, you get 1/2 BC sine theta. All this stuff, a lot of it just cancels out. All you're left with is A over B. So once you know the ratios are A over B, then that means that of the whole, this is A over A plus B, and that's B over A plus B. So, like, I actually had forgotten the formula, and I re-derived it this afternoon when I was preparing this lecture that way. So, but anyway, that's, and that actually happens to me a lot in contests where I forget a formula, and then I have to re-derive it. But anyway, that's the inter-angle bisector rule. So if you can remember it, then all it is the ratio of the areas of the two things, as long as you know that these two angles are the same, is equal to the ratio of these sides. All right, any questions about the angle bisector rule? All right, next, coordinate system. So a lot of times what they'll do in a problem, they'll just give you, like, here's triangle ABC, and they give you some information about it. And they'll be like, oh, there's a square that's off the side over here, and then there's some circle over here. They just give you a bunch of stuff. Right? So one cool thing that you can do is, in some problems, fix some point to be 0, 0. Right? And then maybe this, you know what length this is, so this is going to be like x comma 0. And then what you can start doing is utilizing the piece of information in the problem to figure out the coordinates of all these points. And then once you know those coordinates, things like distance and areas are actually not very hard to find. Because now you can just use like Pythagorean distance formula and other things like that. Right? So I don't have a specific problem right now, but basically the whole idea of a coordinate system is to take a problem where they don't give you x, y coordinates and plot the figure arbitrarily, make usually 0, 0 is what you like as a point of reference, because more than often we end up having to do distance formula. And if you can subtract 0 from something, that makes distance formula a little bit easier, right? Where you pick your points to be, it's more of an art than a science, right? So, but depending on where you pick what point to be, once you pick 1 point, everything else is forced for the most part. Or 2 points rather. Once you pick 2 points, everything else is forced. But that's kind of an art. So you get better at it the more you do it. Like the first 5 times you do coordinate systems on problems, probably won't be very good at it. But the more you do it, the better you slowly start figuring out, oh, last time I did this, this didn't work out. And you try something else, and eventually you get better at it. All right, any questions about that? Okay. All right, next we have this idea of 3D visualization. And this is kind of hard to do, all right? A lot of times they'll have these problems where you have some, they'll be like, oh, take the sheet of paper and fold it and then make a cube out of it, right? Or something like that. And these, I don't know how to teach this. You just have to try really hard in your head to visualize things. Sometimes you can map to a coordinate system, but a lot of times what you have to do is just envision what's happening. All right. What I'm going to try to do is I have one example problem, and there was a really cool problem I did a few weeks ago, and it eludes me now where I found it. The problem is a lot of times what will happen is you'll do a problem and you just can't remember where you found it. So right now I have 2 problems that require some level of 3D visualization. And I'm going to do those 2 for you. If I can remember in my head where I got the 3rd one, then maybe I'll send her. Last time what I did was I went over a bunch of problems last time. Did you send out the
Yes, I sent everyone, yep, everyone got the...
Cool, yeah. So same thing, if I can find a couple more problems that require 3D visualization, I'll just send out like the problem in my typed up solution to you guys. Okay, and then finally the median rule. There's probably multiple median rules, but in doing one of the problems I had to use one of these median rules. And that is if I've got some triangle. So a median is basically you go from one segment to the middle, so this is like x and x. And I go, let's say like this, and this is y and y. Okay, and then the medians all meet at a point, and this is like, my 3rd median is a terrible median, but I swear they meet at a point. All the medians meet at a point. So what happens when the medians meet at a point? So let's take a look at this point. Let's take a look at this length right here. This is going to be, let's say this whole length right here is L. This is L over 3, and this is 2L over 3. And this is going to be true for all 3. The median is that line segment that starts at a vertex and goes to the opposite side. So the point where the medians meet, this is 1/3 the length of the whole median. Okay? So this is useful then because this is the base of a triangle, and if this is 1/3 of the way up to like where the altitude would be, the area of this is 1/3 the area of the whole triangle. Okay? So that's the median rule. It's helpful in problems where you have medians and you're dealing with areas, as you might imagine, because it gives us a relationship between the median and an area. So, all right, any questions on that? So, like I said, all these rules are typically taught to you in just regular high school geometry course. All right. Now, when you see some of these problems, you're gonna be like, "Whoa, I didn't learn how to do that." So, I'm gonna start taking you through some of the ones I've got planned. All right. So the first problem, number 8. Sure. Okay. So they draw a big picture of a big triangle. It's isosceles, even though I didn't necessarily draw it that way. And they have like a little okay, well, it's not perfect. 1, 2, 3, 4, 5, 6, okay. So they draw this big triangle. And they call this point D, and they call this point E, and they call this point A. I'm going to guess this is B, and this is C. I forgot to look, but I'm going to guess this is what they are. And they tell you that it's isosceles, so AB equals AC.
Yeah.
What else do they tell you? It says each of the smallest triangles has area, so the whole area ABC, they tell you is 40. They tell you all the small triangles that I drew in that middle row there have an area of 1. So small area, whatever. Small area equals 1. And then they say, what is the area of trapezoid BCED? Question mark. So your goal is to find that area. The area of the whole thing is 40, and the area of each of these is 1. Okay? And these are all similar. So they're not just random triangles, they're similar. And so naturally what you want to do is you want to continue drawing in these similar triangles. And what you realize is that as you draw these similar triangles in levels, right, these are all parallel lines, and you can continue drawing them. Like you can basically, they're parallel lines here, 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 and so on. Right? So what you can see is because of all these parallel lines and because these are congruent, they tell you each of these are congruent, of course, all with area 1. Then all these all up here all have to be congruent. You can use the parallel line rules, like parallel line cut by transversal, blah, 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 to prove that those are all the same triangles. So since these are all the same, the area of each of these is 1, and this is going to be 16. So the area of this top is 16. And once you know that, then if you know the whole thing is 40, then just 40 minus 16 is 24. So the key here is drawing in those parallel lines, and then once you draw in those parallel lines, what you find is that because of the spacing of those lines, those triangles are all the same. They're all congruent triangles, and then it all works out. So, any questions on that one? And that one's an easier question. That was number 8 on the AMC 12 last year. AMC 12. All right, the next one, I like these. These are folding. It's a folding question. Everyone's favorite triangle, the 3, 4, 5. They have way too many 3, 4, 5s in this particular set. And one thing, just so you guys know, it's always good to memorize like a bunch of Pythagorean triples. All right. And as a sidebar, so you should I'll just put up some of them that I just know. Obviously, any multiple of one triple is a triple.
9, 40, 40.
Yeah.
Yeah.
So basically, you'll notice there's a pattern. Yeah, that's a good one too. There are a few others, but this probably covers like 80% of the ones. Let me see if there's something else I'm missing. Obviously, like any multiple of this one, 12, 16, 20, blah, blah, blah. Any multiple of that one, 9, 12, 15, and so on. But anyway, so here's my 3, 4, 5. And they tell us that we're going to fold. So this is, they give them names, of course, A, B, A, C, B, A, B, C. So we're going to fold A to point B. So we're gonna take B
or B to A, I think is how they say it. So we're going to take the point B and we're going to fold it to A. So I'm going to take B and I'm going to fold it so it folds to A, so it lines up exactly. So the fold is going to happen halfway across, right? So this is 2.5 and this is 2.5. And since it's a fold on a line, it's going to be perpendicular. Everybody okay with that picture? Okay. The question that they ask, what do they ask us here, is that when you make the fold, it creates a crease in the paper, and that creases the line that I've drawn. And they want to know what is the length of the crease. Okay. So you'll notice, yes, it's a similar triangle, right? So this is a 3, 4, 5. And then this is a right angle, and this is the same shared angle, right? So this guy right here is similar to the 3, 4, 5. Okay. So the ratios of the sides, right? So this is basically, I'll write it in, maybe I'll write it in a different marker color. So this is like 3x, this is like 4x, and this is like 5x, right? So the ratios, this is the short side because it's across the angle, right? That's the smaller of the two angles. So generally speaking, as long as your drawings aren't terrible, we're dealing with right triangles, I just do which one looks like the small angle and which one looks like the big angle. And as long as my drawing hasn't gone, so what I do with the triangles when like it's close to 3, 4, 5, I draw one side like way shorter than another side. I intentionally make my drawing off so that I'm less likely to screw up the small angle versus the big angle. Okay? So just a little weird tip that like I use so that I would reduce my chance of screwing stuff up. So anyway, it's clear that this is across the small one. So this is just 3/4 of the 2/5, or 2.5. So we have 5 over 2 times 3 over 4. That's going to give me 15 over 8. And that's going to be the length of the crease. Okay. So whenever you're folding a point like that, it's always going to make a right angle. And then now that we have a right angle, we have a similar triangle. So. All right, any questions on this one? Everyone over there good?
We're good. We're good.
Cool. Okay. All right. I will erase.
Oh, hold up. I'm sorry. What was the question about this one?
The question was how long, if you fold point B to point A, how long is the crease on the paper?
Okay, that's cool.
Yeah.
Thanks.
All right. Okay.
It's like almost I know.
Oh, this one's good. Okay. So can I erase this?
Go ahead. This is a good question. It's going to be question 13 from 2000.
Okay. So yet again, I think the question writers were really enamored with the 3, 4, 5 last year. We've got another 3, 4, 5 triangle, and it turns out that this is a farming plot. So so these are like you grow corn or something like that. And there's a small square that's unplanted, right? So maybe the farmer can stand here and admire his crops. So it's a small square and it's called S. And then what we're going to do is from the corner of S to the this is, I guess the farmer wanted it to be like the right angle symbol. That's why he didn't put crops there. That's the story that they tell us. And then, so now we know, they also tell us that if we were to take the shortest line distance to the hypotenuse, this shortest line distance is 2. Okay? And that 2 forms a right angle, of course, because it's shortest distance, right? If it wasn't a right angle, then it wouldn't be shortest distance. So you have to make it shortest right angle there. Okay. So now the question is, what fraction of the field is planted? So the planted is everything but the square. Little square, we'll call it. Okay? All right. So if you remember from the last problem, whenever you've got a parallel line in a right triangle or a perpendicular line from a right triangle going down like that, where are we going to form a similar triangle? What would I have to do to form a similar triangle? What's that?
Both of them are similar triangles.
Yeah, we got it. We could get two of them. Which one probably makes the most sense for me to draw in?
Smaller.
The smaller one? And what line do I have to draw in? Which direction should I go from this point?
I think we would go to the right angle. I mean.
So I start here.
Oh wait, no, you would go to the one at the top.
I want to go up.
Yeah.
Okay.
You tell us.
So we go. So the key to these problems is figuring out what line to draw in. Okay. I'm going to go over why that's the right line to draw in. Okay. So this triangle right here, do you agree that this triangle is similar to the 3, 4, 5? Yeah. So the reason that it's similar to the 3, 4, 5 is we've got this right angle, and this angle going down, this is kind of this part of the square is parallel to this right here, right? So it's as if I cut it off here, right? So if I cut this off like so, it's easier to see that this and this is similar to this guy right here. It's a classic picture, right? They're all similar. And so now what I want to do is once I know that this is similar, this is really easy for me. This is the longer leg. Do you guys agree that's the longer leg? It's across the bigger angle and that's the smaller angle. So that means that this guy, okay. And what does that mean this guy is right here? 2.5, right? So it's a 3, 4, 5 ratio. This is my 4, so this is my 3, and that's my 5, and that's 2.5. Does everybody follow me there? All right, so we're almost done with this problem. What haven't I done yet? Okay, so that's the hardest part. What we just did right there is the hardest part of the problem. I would say the rest of the problem kind of writes itself. What should I do next? And remember, that's a square right here. This S is a square. Yes?
You have the 3, so you subtract 2.5, and that's the side of the square. Or is it not?
It's actually not, surprisingly. Why? Okay, so a really good thing would be to debug. Debug is when someone makes an error, which actually looks like a pretty good suggestion. Let's figure out why. So the suggestion given was the square is 0.5 because I can take 3 and subtract out 2.5 to get this. What's the error? Yeah, 2.5 stops right here. Do you see where it stops? It stops just a little bit short of up there. Because this triangle is not 3, 4, 5 physically. It's something less than 5, and its height is something less than 3. We don't quite know what it is, but it is more than 2.5. Right? Something more than 2.5. So what happens sometimes when you make small pictures, you can make small errors like that. Okay? And I guarantee you that there's an answer in here that where if you plug in 0.5 for the side of the square, that's going to be one of the wrong answer choices. Because that's like probably a common error that people make. Okay, so it's not 0.5. And what I would say is that when the problem writes itself, you don't know what it is yet, but you will find it out. So if we don't know what something is, what should we do? And we care about it, what should we do?
A variable.
A variable. So what do you guys want to call the side of the square? Oh my goodness. I'm going to call it A. Okay. So now, how tall is this rectangle right here? The dotted one. How tall is it? What is it? 2.5 plus A. So that's this side of the, not rectangle, I said rectangle, I meant triangle.
Isn't that a trapezoid?
How long is this guy right here, this side of the triangle? 4 minus A. What do I know about the ratios of these sides in this triangle? 3, 4, 5. So this is 3x, and this is 4x. Okay. So now all we got to do is just set up, however it is you want to do it, doesn't really matter. 4 minus A over 2.5 plus A equals 4 over 3. Then we'll get 12 minus 3A equals 10 plus 4A. Then we get 7A equals 2, and A equals 2 7. Okay. So basically, this problem is all about similar triangles. Similar triangle number 1 is where you carefully draw this dotted line. Similar triangle number 2 is if you follow the dotted line all the way down and go all the way across and give a variable name to the length of the side of the square. Right? So these are all like classic things, right? The most important thing is that if you don't know what something is and you care about it, you give it a name. And once you give it a name, you can set up equations for it. And then your goal, of course, is to solve for the it, right? And these sorts of pictures are classically, they just have a ton of similar triangles floating around. So the key is to focus on the ones that matter. All right, any questions about this one right here? And it's, just so you know, on this problem, it's super easy to get screwed up and do like a ton of computation. For about 30 seconds, I started giving this a coordinate, a comma a. I gave like a sine cosine over here. I did an equation of a line, like this is like 4x plus 3y or whatever equals 3 or something like that, or 12. And then I tried to do the line-line intersection to figure out the coordinates of that. I started setting it up, and I was like, wait a second, this looks ugly. I was like, wait a second, let me draw in a little dotted line. And then as soon as I drew in that dotted line, I was like, oh, yeah. So, but that's one thing to realize with some of these geometry problems especially, is it's very easy to go a path that's a valid path. Like had I gone that path, I could have done 3 pages of work and gotten the answer. It's very easy to get into that trap. And when an easier solution exists. And in a 75-minute contest where you have 25 problems in 75 minutes, right? Time management is super huge. And you almost need to like catch yourself because it's like really alluring to go down that rabbit hole, right? So there's like, oh, I can see it. Like as soon as I started that problem, I was like, oh, I can see the equation of these 2 lines. I just have to do system of 2 equations, get something in terms of A. But the problem is, of course, this is going to be some crazy thing in terms of A with square roots, right? And that's going to be very difficult, even if there's only one variable in it to solve for that, right? And so it's important when you're taking tests to be really cognizant of time management, right? And what I would say is, like, let's say you utilize the fact that, hey, this one's problem 17, and if you feel like you can do a couple more, right, then you say, okay, this is going down the wrong rabbit hole. I can't spend more than a minute on it. I'm going to leave it be, go on to something else, maybe come back, I'll see something more elegant. Or the other thing, what I actually did when I was working on it, I just stopped myself from going down that path and asked myself, hey, can I see something cleaner, right? So those are your 2 approaches, is when you think you're going down a rabbit hole, you only want to go down it if you know you're not going to get more than one more problem in the whole set, and you've got like, say, 7 minutes, and you think you can finish it in those 7 minutes, right? So I definitely would, like, what's the word? I definitely grinded on problems where I just got them because I did like 5 times as much work as somebody. But you don't want to do that too often. It's only worth doing if you can't get anything else and you're pretty sure that you can see how the problem is going to turn out. Okay, any questions before I erase that? All right, next problem. And this is all from the same contest, like so many similar triangles and so many 3, 4, 5s. I think the guy like left his cheat sheet of Pythagorean triples like at home, and that was the only one he remembered or something. Okay, so we got a triangle ABC with AB is equal to 50. So AB is 50. Did you guys take this one last year? It sounds like you remember.
He did all these a while ago.
I know.
Okay. Who did them? Oh, you did them. Oh, okay. One of the 2 of you did them. Okay. And then AC is 10. What else did I tell you? Area ABC.
This is definitely a Heron formula.
Equals 120.
You could definitely see.
Yes, you could solve for the 3rd side if you know the area using Hero's formula. It would be a pain. Let's see. Let D be the midpoint of AB. So D is in the middle. Let E be the midpoint of AC. So E is like over here. The angle bisector BAC. Okay, so we make the line segment DE. And then, incidentally, if E is the midpoint and D is the midpoint of these 2 sides, what do we know about DE and BC? Bingo. Right. And the area of this guy right here is 1/4 the area of the whole thing, because they're both midpoints, right?
Yeah.
This is a similar triangle, 1/2. So the area of this right here is 1/4 of the whole area. So that shaded area is 30. Let's see here. The angle bisector of BAC intersects DE and BC at F and G respectively. So I draw this little dude right here. This is theta, this is theta, this is F, this is G. There we go. What is the area of FDBG? So we want to find. Okay. So, do we know of any? Are there many simple quadrilateral area formulas?
Base times height.
Yeah. So if it's a kite, then there's a simple one, but we don't know. So the answer to that question is usually no. Like in more advanced contest stuff, yes, they have like direct ways to get areas of quadrilaterals. But on an AMC, unless it's question 24 or 25, you're not ever actually going to find the area of a quadrilateral. What am I going to do instead?
Draw some lines.
I might draw some lines. I'm actually
Divided into triangles?
triangles, right? So areas, yeah.
Oh, you would find like GBA and then you would subtract FOA.
GBA, yeah, okay, sure. Yeah, so the suggestion given was, hey, this quadrilateral can be this triangle minus this triangle. So more often than not, in contests where it's not super hard, anytime you're asked to find the area of a quadrilateral, you never actually find the area of a quadrilateral. You find the area of a bunch of triangles and add and subtract stuff until it makes a quadrilateral. Okay, so this is another standard trick. So there's probably multiple ways to do this. What I decided to do when I started working on this problem is I first noted the median rule, right? So you'll notice that we've got E and we've got D. We've got, that's a median, but I don't really want to draw that one. But we've got the angle bisector rule. So we got these two angles are the same, so we can try to use the angle bisector rule. So we had already noted that area AED equals 1/4 area ABC. So this area right here, AED, is 1/4 of the whole. Okay. Now, the other area that I can get is area ACG. So you'll notice that ACG is the angle bisector. So this I figured out from similar triangles. Right? So the AED is similar to the big triangle, and that's how I got that one. Now ACG, you'll notice this is the angle bisector. So now we can use the angle bisector rule. Right? So this is 10 over here, and this is 50. Technically, this is 5, and this is 25. Okay? So what is going to be the area, what proportion of the whole area is ACG? 1 what? Yeah, 1/6. It's 1 to 5, right? There's 10 and 5, or 10 and 50. So it's a 1 to 5 ratio. So this one's 1/5 of this. So in terms of the total, it's going to be 1/6. So 1/6 area, ABC. So now I've got this guy over here, and I've got this guy over here. If I subtract both of these from the whole, have I subtracted too much? So, right, so now my current idea is let's just do area ABC. Let's subtract out area AED. Let's subtract out area ACG. How am I doing if I do that? What have I gotten the shaded area, or what have I done like slightly wrong?
There's an overlap.
What's the overlap?
AEF.
Yes. What I've done is I've subtracted out AEF twice. So this we know is like 120. This we know is 30. This we know is 20. And what we need is area AEF. So this is essentially what we call inclusion-exclusion principle.
Oh my god, counting.
Yeah, inclusion-exclusion, right? So the idea here is that, hey, we want to get the shaded stuff. Let's subtract from the whole because the quadrilaterals look ugly. So I just keep on subtracting triangles. I subtract a couple triangles. I'm pretty darn close. But then what I've done is I've over-subtracted. Got a little zealous taking stuff out. Put stuff back in. So now we just need to find the area of this guy right here. Now keep in mind, this is parallel to this. So what do I know about this little triangle and this bigger triangle? Similar, yeah. So now we know that AEF is similar to, I forgot the sign for similar, it's some wavy thing, but I'm pretty bad. Similar to ACG. Do we know the area of ACG?
Yes.
The area of ACG
There. 20.
is 20. Okay. And what do we know about the area of AEF? It is 1/4 area of ACG because it's the side length's half. So this is going to be 1/4 times 20 equals 5. So we just put a +5 there, and this is going to give me 75. So this is one of my favorite problems of the ones I did last night. I thought this was pretty cool. So there's probably other ways to do it. There's so many triangle rules that you can utilize. That's just the first way that I did it. I guarantee you there's multiple ways to add and subtract things to get that to work out. Yeah?
How do you know ACG is 1/6 of ABC?
So the way ACG, this is angle bisector. And do you remember the angle bisector rule? Is the area of the triangle to the left and the area to the triangle on the right, the ratios are equal to the ratios of the sides. Do you remember that rule?
Okay.
I called it angle bisector rule,
Okay.
right? So when I got a 10 here and a 50 here, right? And then I split by the angle bisector, the area, this is the one where I did the proof for you guys, like the area of this triangle is 1/2 10C, and the area of sine theta, and this one's 1/2 50C sine theta. So everything cancels except for the 10 and the 50, so the ratios are 5:1. So the whole area is like 60, right? This gets 10 of it, and this gets 50 of it, 60. So it means this area is 1 out of 10. It's basically, I wrote it as A over A plus B when I wrote the formula, so it's 10 over 10 plus 50, which reduces to 1/6. So that's where that comes from. Yeah.
Do you find that AEF is 1/4 of ACG in the same way that AED is 1/4 of ABC? Or
What, this 1/4?
the second 1/4?
Yeah, it's the same
Same
method.
thing. So basically, F is the midpoint of AG.
What's that?
F is the midpoint of AG. Or
F is it the midpoint of AG?
yeah, I mean, how else would you find it?
Should be, yes.
Okay.
Yes. Yeah. So there's probably another way where you just directly subtract this triangle out.
Oh, okay.
Yeah. Actually, yes. Okay, so let's do it that way. Just so, okay, so the triangle, yeah, that's good that you mentioned that. Area AGB, right, is going to equal 5, 6 times 120, right, because this is the 50 and the 10. So that one was 1/6, so this one's 5, 6. So the area of this whole thing is 100.
Yeah.
Okay, and then we just need to subtract this one out, but this is similar to the whole thing. So it's 1, but it's like scaled down by half. So minus 1/4 times 100.
Yeah.
So that's 75. So that might be a more direct way to do it.
All right.
Yeah. So that like in this way, there's no inclusion exclusion.
Sure. But what I'm asking is how can you be sure that F is the midpoint of AG?
What's that? Why is it the midpoint?
Yes.
Because it's a similar triangle thing. Everything is a scale. Think about a map, right? And you're stretching the map out, right? So AED is like, I basically did a linear shrink to ACB. So every linear thing that's like a line that you could walk on it shrinks by that same constant ratio. Any line, right? So imagine that I had a piece of paper. This is what it means for two things to be similar. And I can take any arbitrary line on that piece of paper. Now imagine that you had some machine that shrinks it. Everything is going to shrink by the same factor. So this is just AFG. This is just the line on AG is the line on the big triangle. When I shrink it in half, it becomes AF. Does that make sense?
Yeah.
Yeah. Okay. So that's the reasoning behind it.
Gives a sense of
So yeah, I mean the cool thing about similarity is like think about like intuitively what it would make sense on a map, right? Any path you walk on a map, right? If a map is 1/10 scale, then you're walking 10 times longer than like the map path. Any linear path. Yeah. Okay, let's see here. And now, so those were from. So now I'm going to go to the packet, and I'm going to. I didn't have time to do all the problems in the packet, but I did a few of them. So for those of you who have the packet handy with you, the first one I'm going to go to is Geometry 3.
Okay, you guys didn't get this packet. This was for last time, so I'll
Okay.
email it to you. But your teacher might have it. It's from the AMC topical quizzes. Did she give it to you?
I don't think so. But
Okay, so I will email you.
Okay.
I will email the TC.
I'll put the problems up here just like I'm doing with
Yep.
the other ones. So can I erase this?
Yeah.
Okay. Okay.
Were there any plates left? Were there any plates left by chance?
Yeah, I think that, right, that's a clean plate?
That's a good idea.
This was a foul, actually.
There you go. I literally just passed that.
So this is another bad drawing of mine.
Okay.
So they tell you that ABCD is a rhombus, even though mine really does not look like one. And they tell you that the angle DAB is 60 degrees. And then they tell you that BFDE is also a rhombus. And it's a similar rhombus, it also has 60 degrees, right? So they tell you that both rhombuses are similar to one another. They also tell you that the area of ABCD, so area ABCD is equal to 24. And then they want to know what is the area of BFDE. They're going to say question mark. What is the area of that small rhombus? And keep in mind that small rhombus is similar to the big rhombus. Okay. So we don't know what the side is. Maybe what I'll do is I'll label S as the side of my rhombus. Now, if I label S as the side of my rhombus, I probably want to know the diagonals. It's pretty clear that the small diagonal is just, what's the small diagonal? S, yeah, why? Equilateral triangle. A rhombus with 60 and 120 are two equilateral triangles, right? So like if I split this angle in half, that's a 60, 60, 60. That's another 60, 60, 60. So yeah, small diagonal is S. I want to figure out the big diagonal. So I know, so the small diagonal in the big figure is S. Let's figure out the big diagonal. So the big diagonal, basically I've got S and S. The big diagonal is here. And when I got a 120, I always want to just draw this like nice little bisector. And it's got this nice property that because everything's nice and symmetric, this is going to be 60 and this is going to be 60 and this is going to be 30. And we got a 30, 60 negative.
Oh.
Everyone's favorite. So this is, what's this length right here, this small dude right here?
S root 3 over 2.
Right. And so the large diagonal is going to be S root 3. So you'll notice that the small diagonal of the big rhombus is the large diagonal of the small rhombus. Right? So the ratio of the areas, area of BFDE divided by area of ABCD is simply equal to S over S root 3 squared. Right? So if the similar sides, the corresponding sides are S and S root 3, then the corresponding areas are always going to be squared. So you just take the ratio of the sides and square them. And the s's, of course, drop out. What do I get as my fraction? 1/3. And then that means the area of the small one is 1/3 the area of the big one, which means 1/3 times 24 equals, to answer their question, what is the area of BFDE? It is 8. All right. So again, it's pretty much just similarity. There's nothing else in this problem except for similarity and then, of course, 30, 60, 90s. So they've finally moved away from 3, 4, 5s. But this is a different year. So. Okay. All right, let's see here. Question number 3.
I know you explained that before, but
Yeah.
why is the small diagonal S again?
Because,
Something with equilateral triangle?
so this is a rhombus.
Yeah.
And when you draw this diagonal, because everything's symmetrical, it's going to split the angle exactly equal. And since this is a 120, that's going to be 60 here.
Okay.
And once I know that this is 60 and this one's 60, that one has to be 60. And of course, it's 120 and 120. And once you have 3 60s, it's always equilateral. So, all right. Can I erase? All right, let's see here. Okay, so we have a square ABCD. Where do they draw all their little funny names. So they drew A up here. B, C, D. Then after they draw the square, they decide that it's a good idea to draw a point E somewhere out here. And E is collinear with B and D, so B, D, E makes a line. And then they decide to draw a nice fun circle right here. And then they decide that it would be a good idea to draw a point of tangency from A to the circle called F. And they tell you that the side length of the square is S and the radius is R. Tell you that. And then they ask you the question. Oh no, they tell you more. They tell you that AF, that line right there, that has the length of, and it's a beautiful length, it is the square root of 9 plus 5 root 2. They also tell you, yeah, sarcastic. They also tell you that R is a rational number, and they tell you that S is a rational number. They're both rational numbers, R and S. And then what do they want to know? They want to know what is R divided by S. Okay. All right, so this looks like a pretty ugly picture. And so remember what I mentioned to you guys, I don't have a problem, but this idea of putting things on a coordinate system. Okay. So this is an awesome picture to put on a coordinate system. And why do I think it's an awesome picture to put on a coordinate system? Because there's more to it. What lends this picture to be very nice on a coordinate system? All right, so something triggered in my brain like 2 seconds after I looked at this picture going, let's put this on a coordinate system. And why did my brain trigger that thought? Yeah, squares are super easy on a coordinate system. 0, 0, 0, comma S, S, comma 0, S, comma S. Right? So squares are very easy, and then circles are pretty easy in a coordinate system as well. Right? X minus like some value squared plus y minus some value squared, and so on. Right? So yeah, so I want to do a coordinate system. I'm going to make this 0, comma 0. This is going to be S, comma S. And the beauty is, because it's a square, this is a 45-degree angle. More importantly, what's the slope of this line? It's 1. So 1 is really important because now what that means is that when I move from D to E, my delta x and my delta y are the same. So that means that this delta x is r over root 2, and delta y up here and delta x down here is r over root 2. So what that means is the coordinates of the point E is nothing but s plus r over root 2, and again, s plus r over root 2. So I got the coordinates of the point E. That's very helpful. I've also got this point right here. This is going to be 0, comma s. Okay. So I got some different things in this picture, and remember, ultimately, I need to know something about my picture, right? So I need to, they tell us that AF, right here, is square root of 9 plus 5 root 2. So I have to use that information somehow, and I thought a good idea to do that is to draw this in. We know that this is a right angle because it's a point of tangency. Agreed? So now I know that AF squared plus r squared, because that's a radius, is equal to AE squared. Okay. So now AF squared, I can plug in, is like 9 plus 5 root 2 plus r squared equals AE squared. Now, this is not very helpful because AE squared is an unknown and r is an unknown, and I have no s in the formula. So there's two things that we need to do. We need to introduce an s. How on earth am I getting the ratio r over s if there's no s in my formula? And secondly, I kind of need to get rid of AE squared. Okay. So what might be a good way to get rid of an AE squared? Get another triangle, yeah. And so now you can see that AE, more naturally, we can do distance formula between A and E, right? And that this right triangle is kind of this right triangle right here. Ultimately, AE squared is going to be nothing but this length right here, which is s plus r over root 2 squared. And then plus this length over here, plus r over root 2 squared. Okay? So now we have exactly what we want. No AE and a single equation with r and s in it. So let's see what happens here. S squared plus 2rs over root 2 plus r squared over 2 plus r squared over 2. So this is pretty awesome. My r squareds just all fall out. They're done. Right? This is an r squared here. There's an r squared here. Gone. Pretty awesome. Okay. We, however, still have some problems. Maybe I'll rewrite this. It's 9 plus 5 root 2 equals s squared plus rs root 2. At this point, you might be tempted to factor some stuff, right? We might factor an s out. Another thing that I almost immediately thought of is if I'm just solving for the ratio r over s, maybe I can divide the equation through and rewrite it in r over s, right? So classic trick is when you have something like this, divide by s squared, right? If we divide by s squared, the right-hand side is beautiful because that becomes a 1, and this becomes an r over s. Anytime you see an rs and you want to do things in terms of r over s, you just multiply or divide by either r squared or s squared, and that usually works. But unfortunately, the pesky thing is that even though the right-hand side works out beautifully, the left-hand side becomes a mess because it's an over s squared and there's no r over there. Okay. So at this point, we need to invoke a piece of information that at the time that it was given to us seemed completely irrelevant. So what piece of information, maybe when you read the problem, or I told you a problem, you're like, why is he telling me that? What piece of information have we not yet used that you might have even questioned, well, this is odd. Why would someone state this in the problem?
RNS is rational.
Rational, yeah, exactly. Okay. So here's the deal. If you've got numbers that are rational, they can't form a square root 2. There's closure in rational numbers. A rational times a rational is rational. Okay? A rational divided by a rational is rational. Add, subtract. There's closure in rationals. So anytime we want this equation to be true, we have to equate. This has to equal that, and this has to equal that. So we just say 9 equals s squared. Since s is positive, s is equal to 3. And then we just say 5 root 2 equals rs root 2. Because r and s are rational, that has to cancel out. And we have 5 equals 3r, and r equals 5/3. And then finally, to solve for the ratio, r over s. Well, r is 5 over 3, and s is 3, so you get 5/9.
What did I say after? I called it.
So this happens. Right? So anytime, this is one of those things, and this is actually one of the commonalities between, we were talking about differences between math contests and programming contests. This is huge in programming contests, where they tell you some weirdo thing, and you're like, why are you telling me that? Why are you telling me that that number is less than 81? Right? Just like a constraint on the input or a constraint on the variables, that's just bizarre. Like, why did you tell me that? Right? And the reason they told you that is when you don't know it, it's going to be critical to finishing the problem. It's never going to be something that you use right away. It's almost always going to be a detail that you ignore and don't use. And then later, when you get to a juncture where you're stuck, you end up using this critical fact that was like one super tiny like phrase within a sentence to crack the problem. And that's what happened here. And that's kind of the classic. They have formulas for like the sum of the roots and the product of the roots, which some of you might be familiar with, some of you might not be familiar with. But the way we get those is by, if you have two polynomials that you know are equivalent polynomials, you can equate coefficients to each of the terms. In order for two polynomials to always be equal, we equate coefficients of each term. Here, because of the rational restriction, these are essentially forced to be essentially separate terms in a polynomial, where I can then equate coefficients. All right, any questions on that one? Okay. So a few things that are really cool about this problem that are kind of what I would say, quote unquote, takeaway points. Takeaway point number one is that there are sometimes telltale signs of when you want to take a geometry picture and put it on a coordinate system. And the telltale signs here were that it's really easy, the figure is such, with a square and a circle, where it's really easy to calculate coordinates of points. Okay? And then the second kind of salient feature here was this. They had some weird piece of information that you initially ignored, and then the time to think about it or go reread the question is where you feel like you might be stuck, right? That piece might be that final piece to crack the puzzle. All right, any questions on this one? All right, let's see what's the next one I've got set up. This is called Geometry of Circles. There we go. Okay. And this is one of I like these. Okay, can I erase? Good to erase?
Imagine like designing this question.
So we have 3 circles of radius 2. So now we're going to move to circles instead of triangles. So oddly enough, in this one, a triangle comes up. So the radius is 2. And they don't draw any lines in. But what they do is they shade everything. So everything's shaded. It's a little funny, not triangle, like a little curved in triangle. They want you to find the total area, shaded area. And it's got like 3 circles. They're all radius 2. Okay. So let's go ahead and draw in the radii. And what do you notice, if this is 2, what do you notice about these 3 sides of the triangle?
Equilateral.
Equilateral. And if it's equilateral, what does that tell us about the angle? 60 degrees. So now what we can do is we can take the area of the triangle. We're going to find the full shaded area. The area of the triangle. Okay. Do you guys know the area of the equilateral, the formula for the area of the equilateral triangle?
Yeah.
Yeah, s squared, square root 3 over 4. You can, of course, derive it, right? So if I've got an equilateral triangle, this is s, I draw this. This is s over 2. This is s root 3 over 2. You take 1/2 the base, which is s, times the height, which is s root 3 over 2. It's s squared, square root 3 over 4. This comes up so often in contests, like it's helpful. Again, 25 questions, 75 minutes. Super helpful to have it memorized. Okay. So yeah, so this area is then going to be 4 squared over 4 times square root 3, and this is going to be 4 root 3. So what area is left for me to find?
Minus.
The what?
Minus.
I want to add the circles, right? Because the circles are shaded and the inside's shaded, so I just need the circles on the outside, right? So a full circle, of course, is pi r squared. But then, how much of the circle do we actually? So what I'm going to do is I'm going to erase this because we already counted it. So now I've got a little Pac-Man person up here, right? How much is this Pac-Man person of the whole circle?
5.
Yeah, 5/6. So Pac-Man
Wait, we're done.
equals 5. Yeah, we're done. 5/6 of the full circle.
15/6.
Yep. So 3 Pac-Mans is, yes, 15/6. And the full circle was pi, and then r is 2 squared. And then it's 15 times 4 is 60. 60 divided by 6 is 10. So this is 10 pi. So my total area is 10 pi plus 4 root 3, which was one of the answers.
So I knew it. I was thinking that. I was like.
Okay, so this one's in the geometry section, but it's really not much of a geometry problem. But that happens, right? There's always mixing these things. So, can I erase this right here? So, Mary divides a circle into 12 sectors. So we're going to,
That's 30 degrees each.
12 sectors. The angle measures are in arithmetic progression, and they are all integers, integer in degrees. So it's an arithmetic progression. The angles are all integers in their degree, number of degrees. What's the smallest possible